directly for main propulsion, with generators providing auxiliary power, or else employ turboelectric transmission, where the steam drives a turbo generator set with propulsion provided by electric motors. A limited number of steam turbine railroad locomotives were manufactured. Some non-condensing direct drive locomotives did meet with some success for long-haul freight operations in Sweden and for express passenger work in Britain, but were not repeated. Elsewhere, notably in the United States, more advanced C designs with electric transmission were built experimentally, but not reproduced. It was found that steam turbines were not ideally suited to the railroad environment, and these locomotives failed to oust the classic reciprocating steam unit in the way that modern diesel and electric traction has done. Operation of a simple oscillating cylinder steam engine. Oscillating cylinder steam engines. An oscillating cylinder steam engine is a variant of the simply expansion steam engine which does not require valves to direct steam into and out of the cylinder. Instead of valves, the entire cylinder rocks, or oscillates, such that one or more holes in the cylinder line up with holes in a fixed port face or in the pivot mounting, trunnion. These engines are mainly used in toys and models, because of their simplicity, but have also been used in full-size working engines, mainly on ships where their compactness is valued. 63. Rotary steam engines. It is possible to use a mechanism based on a pistonless rotary engine such as the Wankel engine in place of cylinders and valve gear of a conventional reciprocating steam engine. Many such engines have been designed, from the time of James Watt to the present day, but relatively few were actually built and even fewer went into quantity production. See link at bottom of article for more details. The major problem is the difficulty of sealing the rotors to make them steam tight in the face of wear and thermal expansion. Their resulting leakage made them very inefficient. Lack of expansive working, or any means of control of the Q-taff, is also a serious problem with many such designs. By the 1840s, it was clear that the concept had inherent problems and rotary engines were treated with some derision in the technical press. However, the arrival of electricity on the scene, and the obvious advantages of driving a dynamo directly from a high-speed engine, led to something of a revival in interest in the 1880s and 1890s, and a few designs had some limited success. Of the few designs that were manufactured in quantity, those of the Hult Brothers Rotary Steam Engine Company of Stockholm, Sweden, and the spherical engine of Beecham Tower are notable. Tower's engines were used by the Great Eastern Railway to drive lighting dynamos on their locomotives, and by the Admiralty for driving dynamos on board the ships of the Royal Navy. They were eventually replaced in thus niche applications by steam turbines. Line drawing of a sphere suspended between two uprights forming a horizontal axis. Two right-angle jet arms at the circumference expel steam that has been produced by boiling water in a closed vessel under the two uprights, which are hollow and let steam flow into the interior of the sphere. A neolipile rotates due to steam escaping from therms. No practical use was made of this effect. Rocket type. The eolipile represents the use of steam by the rocket reaction principle, although not for direct propulsion. In more modern times there has been limited use of steam for rocketry, particularly for rocket cars. Steam rocketry works by filling a pressure vessel with hot water at high pressure and opening a valve leading to agitable nozzle. The drop in pressure immediately boils some of the water and the steam leaves through a nozzle, creating a propulsive force. 64. Ferdinand Verbiest's carriage was powered by a neolipile in 1679. Safety. Steam engines possess boilers and other components that are pressure vessels that contain a great deal of potential energy. Steam escapes and boiler explosions, typically BLEVs, can and have in the past caused great loss of life. While variations in standards may exist in different countries, stringent legal, testing, training, care with manufacture, operation and certification is applied to ensure safety. Failure modes may include overpressurization of the boiler, insufficient water in the boiler causing overheating and vessel failure, build-up of sediment and scale which cause local hot spots, especially in riverboats using dirty feed water, pressure vessel failure of the boiler due to inadequate construction or maintenance, escape of steam from pipework /boiler causing scalding. Steam engines frequently possess two independent mechanisms for ensuring that the pressure in the boiler does not go too high. One may be adjusted by the user, the second is typically designed as an ultimate fail-safe. Such safety valves traditionally used a simple lever to restrain a plug valve in the top of a boiler. One end of the lever carried a weight or spring that restrained the valve against steam pressure. Early valve could be adjusted by engine drivers, leading to many accidents when a driver fastened the valve down to allow greater steam pressure and more power from the engine. The more recent type of safety valve uses an adjustable spring-loaded valve, which is locked such that operators may not tamper with its adjustment unless a seal is illegally broken. This arrangement is considerably safer. Lead fusible plugs may be present in the crown of the boiler's firebox. If the water level drops, such that the temperature of the firebox crown increases significantly, the lead melts and the steam escapes, warning the operators, who may then manually suppress the fire. Except in the smallest of boilers, the steam escape has little effect on dampening the fire. The plugs are also too small in area to lower steam pressure, significantly depressurizing the boiler. If they were any larger, the volume of escaping steam would itself endanger the crew. Steam cycle. Flow diagram of the four main devices used in the Rankine cycle. 1. Feed water pump. 2. Boiler or steam generator. 3. Turbine or engine. 4. Condenser, where Q equals heat and W equals work. Most of heat is rejected as waste. The Rankine cycle is the fundamental thermodynamic underpinning of the steam engine. The cycle is an arrangement of components as is typically used for simple power production, and uses the phase change of water, boiling water producing steam, condense injects exhaust steam, producing liquid water, to provide a practical heat-forward/power conversion system. The heat is supplied externally to a closed loop with some of the heat added being converted to work and the waste heat being removed in a condenser. The Rankine cycle is used in virtually all steam power production applications. In the 1990s, Rankine steam cycles generated about 90% of all electric power used throughout the world, including virtually all solar biomass, coal and nuclear power plants. It is named after William John Macquorn Rankine, a Scottish polymath. 65. The Rankine cycle is sometimes referred to as a practical Carnot cycle because, when an efficient turbine is used, the TS diagram begins to resemble the Carnot cycle. The main difference is that heat addition, in the boiler, and rejection, in the condenser, are isobaric, constant pressure, processes in the Rankine cycle and isothermal, constant temperature, processes in the theoretical Carnot cycle. In this cycle, a pump is used to pressurize the working fluid which is received from the condenser as a liquid, not as a gas. Pumping working fluid in liquid form during the cycle requires a small fraction of the energy to transport it compared to the energy needed to compress the working fluid in gaseous form in a compressor, as in the Carnot cycle. The cycle of a reciprocating steam engine differs from that of turbines because of condensation and evaporation occurring in the cylinder or in the steam inlet passages. 56. The working fluid in a Rankine cycle can operate as a closed-loop system, where the working fluid is recycled continuously, or may be an open-loop system, where the exhaust steam is directly released to the atmosphere, and a separate source of water feeding the boiler is supplied. Normally water is the fluid of course due to its favorable properties, such as non-toxic and unreactive chemistry, abundance, low cost and its thermodynamic properties. Mercury is the working fluid in the mercury vapor turbine. Low boiling hydrocarbons can be used in a binary cycle. 66. The steam engine contributed much to the development of thermodynamic theory. However, the only applications of scientific theory that influenced the steam engine were the original concepts of harnessing the power of steam and atmospheric pressure and knowledge of properties of heat and steam. The experimental measurements made by Watt on a model steam engine led to the development of the separate condenser. Watt independently discovered latent heat, which was confirmed by the original discoverer Joseph Black, who also advised Watt on experimental procedures. Watt was also aware of the change in the boiling point of water with pressure. Otherwise, the improvements to the engine itself were more mechanical in nature. 14. The thermodynamic concepts of the Rankine cycle did give engineers the understanding needed to calculate efficiency, which aided the development of modern high-pressure and temperature boilers and the steam turbine. Efficiency. The efficiency of an engine cycle can be calculated by dividing the energy output of mechanical work that engine produces by the energy put into the engine. The historical measure of a steam engine's energy efficiency was its duty. The concept of duty was first introduced by Watt in order to illustrate how much more efficient his engines were over the earlier Newcomen designs. Duty is the number of foot-pounds of work delivered by burning 1 bushel, 94 pounds, of coal. The best examples of Newcomen designs had a duty of about 7 million, but most were closer to 5 million. Watt's original low-pressure designs were able to deliver duty as high as 25 million, Butte averaged about 17. This was a threefold improvement over the average Newcomen design. Early Watt engines equipped with high-pressure steam improved this to 65 million. 67. No heat engine can be more efficient than the Carnot cycle, in which heat is moved from a high-temperature reservoir to one at a low temperature, and the efficiency depends on the temperature difference. For the greatest efficiency, steam engines should be operated at the highest steam temperature possible, superheated steam, and release the waste heat at the lowest temperature possible. The efficiency of a Rankine cycle is usually limited by the working fluid. Without the pressure reaching supercritical levels for the working fluid, the temperature range over which the cycle can operate is small. In steam turbines, turbine entry temperatures are typically 565 degrees Celsius, the creep limit of stainless steel, and condenser temperatures are around 30 degrees Celsius. This gives a theoretical Carnot efficiency of about 63% compared with an actual efficiency of 42% for a modern coal-fired power station. This low turbine entry temperature, compared with a gas turbine, is why the Rankine cycle is often used as a bottoming cycle in combined cycle gas turbine power stations. One principal advantage the Rankine cycle holds over others is that during the compression stage relatively little work is required to drive the pump, the working fluid being in its liquid phase at this point. By condensing the fluid, the work required by the pump consumes only 1% to 3% of the turbine, or reciprocating engine, power and contributes to a much higher efficiency for a real cycle. The benefit of thighs is lost somewhat due to the lower heat addition temperature. Gas turbines, for instance, have turbine entry temperatures approaching 1,500 degrees Celsius. Nonetheless, the efficiencies of actual large steam cycles and large modern simple cycle gas turbines are fairly well matched. 68. In practice, a reciprocating steam engine cycle exhausting the steam to atmosphere will typically have an efficiency, including the boiler, in the range of 110%. However, with the addition of a condenser, corliss valves, multiple expansion, and high steam pressure /temperature, it may be greatly improved. Historically into the range of 10-20%, and very rarely slightly higher. A modern, large electrical power station, producing several hundred megawatts of electrical output, with steam reheat, economizer etc. will achieve efficiency in the mid-40% range, with the most efficient units approaching 50% thermal efficiency. It is also possible to capture the waste heat using cogeneration, in which the waste heat is used for heating a lower boiling point working fluid or as a heat source for district heating via saturated low-pressure steam. A steam locomotive AGNRN2 class. Number 1744 at Weybourne NR. Sheringham, Norfolk. A steam locomotive AGNRN2 class No. 1744 at Weybourne NR. Sheringham, Norfolk. A steam-powered bicycle by John van der Riot, in Dortmund. A steam-powered bicycle by John van der Riot, in Dortmund. British horse-drawn fire engine with steam-powered water pump. British horse-drawn fire engine with steam-powered water pump. See also Boyle's law. Compound locomotive. Cylinder. Geared steam locomotive. History of steam road vehicles. Lean's engine reporter. List of steam fairs. List of steam museums. List of steam technology patents. Live steam. Mechanical stoker. James Rumsey. Salamander cause. Steam aircraft. Steamboat. Steam car. Steam crane. Steam power during the Industrial Revolution. Steam shovel. Steam tractor. Steam tricycle. Still engine. Timeline of steam power. Traction engine. Notes. This model was built by Samuel Pemberton between 1880-1890.
Good. I did finish reading. The video splits in 2 minutes and there's a lot of link there. But I think I like just to continue to reading about the boiler. I have to read this like 1 hour. I have to download more links, but I did read it long time ago. But when I back a reader, I did not have any steam engine. So this is why I did like to try to buy a steam engine. I did buy this 50 years old Wilesco D16. It have a 250 milliliter boiler, but just buy a bigger one, half a liter, with a manometer and a water drain. This one you have to turn it upside down. This is a small Wilesco D8. I did buy it because it's special edition with colors. Because maybe I build a Lego set in the future. So this will fit to this colorful Lego. This could make a Lego factory with a steam engine. So this is why I buy all this old part. I could have next to a old steam engine. Could have a car parking there. Or a broken down truck. Could have an old truck next to an old steam engine. Something like this. So I did, and then I get some old, I think that's Wilesco parts. Old part. I maybe need some of the parts maybe. So, but I will continue reading about boiler. So, because I need a lot of time to look the links.